Hello and welcome. In this lesson, we'll learn about the vector and parametric equations of a plane. And to start with, what is a plane? You can think of a plane as a flat surface that extends infinitely far in all directions. To describe a plane mathematically, we use parallelograms, which represent a small part of the plane. To name planes, we use the letter P in Greek, which is pi. Now, before we move on to defining the equations or learning the equations of a plane, we want to take a look at how we can create a plane, physically create a plane. And for this, if possible, it would be useful if you have a cardboard paper and 2 pencils with you so that you can experiment a little bit with that. A plane can be created by a line and a point that is not on the line. So the way this looks is a line and a point that is not on the line. So what I would like you to do is hold your cardboard paper, which represents your plane, place one pencil on your paper and plot a point. If you are able to have the pencil and the point on the same plane, so they would lie flat on the plane, it means that they define a plane. And it's not too difficult as well to kind of envision that if you connected 2 points on this line with the third point that is not on the line, then you would create a triangular shape. And triangles are 2D shapes, which means that triangles lie flat on a surface, which means that a triangle makes a plane. Similarly, we're going to say that 3 non-collinear points, for example, points A, B, and C here, if connected to each other, will form a plane. Again, the way we see it is if we connect 3 points, no matter where their locations are, they would create a triangular shape, which is a 2D shape, which means that it would be able, like the triangle would lie flat on the surface or on the plane. Also, if we have 2 intersecting lines, for example, here is one line and here is another one. So the 2 intersecting lines, if you have 2 pencils and you let them cross each other, then you'll be able to lie the cardboard paper flat on both pencils, and both pencils will be on it, which means that a plane is formed. So both pencils are on a plane. And another way of creating a plane is by 2 parallel, but very careful, they have to be non-coincident lines, which means that we can create a plane by one line in here and another one here. They have to be parallel, right? And non-coincident, coincident, which means that there has to be a space in between. Imagine that if these 2 lines are coincident, that they can't form a plane because they will make a line. So now that we know how a plane can be formed, let's take a look at how we can describe a plane in 3D. So here we are in 3D. We have the X, the Y, and the Z axis, and I drew the plane which I called the plane pi. To describe the vector geometrically in 3D, we are going to use vectors. The first vector we use is what we call the starting vector. The starting vector is named vector R0. And the head of the starting vector will be somewhere on the plane, and I will call the head of it the point P0. We let any point on the plane be what we call the point P, any point on the plane, which means that the point P could be here, could be anywhere on the plane. And we will connect the point P with the origin. So the point P connected with the origin will represent what we call the vector R. And in order to describe the equation or the location of the plane, we're going to use the vector R, which is any vector on the plane, and try to express it in terms of vector R0, which is a fixed vector on the plane. We will know the coordinates of it, P0. And we're also going to use what we call direction vectors, just like we used for the equation of a line. Because a plane can be formed by two lines, we are going to need two direction vectors. Remember what we said, that if we use lines, then we're going to need two of them in order to see where the plane and how the plane is created. I'm going to call the direction vectors A and B. So for example, let's say this is some direction vector A, right? And I'm going to call this one here some direction vector B. So we're going to say that given two direction vectors that lie on the plane and a point on the plane, we'll be able to define the coordinates of any other point on the plane. We're talking about point P. So in order to connect them all together, we're going to work with the coordinates of each. P0, coordinates of direction vector B and direction vector A. So let's start off by connecting the point P0 with point P. So we are going to say that vector R, remember this is vector R, equals vector R0 plus vector P0P. Now we're going to take a closer look at vector P0P. Vector P0P is a vector on the plane, and any vector on 2D can be described or can be expressed in relation to two other vectors, or as the sum of two other vectors that are on the plane. And this is where I will actually moderate this picture a little bit. So what I'm going to do from point P, I will draw a very thin line parallel to vectors A and B. So here will be a line parallel to vector A, and here will be a line parallel to vector B. This would form some parallelogram. So I'm going to make this one a little bit more pronounced. And I hope that you can see based on this that vector P0P, which starts at P0, which is the head of vector R0, and it ends at P, which can be any point on the plane, would be expressed as the sum of this and this vector here, right? So based on parallelogram rule. Now think of what this vector here equals, right? So this vector follows the direction of direction vector B. So it will be a scalar multiple of vector B. So we're going to call this KB. And similarly, we're going to say that this vector here is following the direction of vector A. So that will be vector KA. So we'll say that P0P would equal vector KB plus KA. So remember though that if you looked at the coordinates in here for K, in here we take, and I'm just eyeballing this, about 3 times the vector B, whereas here it seems that we take 1.5 of vector A. So that makes us think that, yes, they would be scalar multiples, but it cannot be represented, they cannot be represented by the same scale, because here we get a different scale of B, and here we get a different scale of A to produce P0P. So now we're going to think Okay, so then we have to come up with a different name for each scalar. So I'm going to call this a scalar t, and I will call the next one the scalar. We use the letter S very commonly, but it doesn't really matter what letters we use, okay? So again, just to summarize everything, we start off with some vector r0. Here goes vector r, which is any vector on the plane. r0 is a fixed vector. So we're going to say that vector r, which is any vector on the plane, can be described as the sum of r0 and p0p. p0p will be on the plane because both p0 and p are on the plane, right? And we're going to express p0p in terms of the direction vectors which are on the plane that we are analyzing here. We build a parallelogram to show how p0p is dependent on a and b. So we express p0p as the sum of a scalar of b and a scalar of a. So now let's take a look at our equation and reformulate it. So r will be this vector, any vector that has a head on the plane. So the coordinates of r can be x, y, z, so any point on the plane. For r0, we'll have fixed coordinates x0, y0, z0. And then we're adding vector p0p, which we just discussed, equals t times vector a plus s vector b, where a and b are the direction vectors. Now for vector a, we're going to use the coordinates a1, a2, a3. For vector b, we'll use the coordinates b1, or we'll name them b2 and b3. So therefore, now the equation will look slightly more complete and more interesting. So we'll reformulate it. So instead of a, we're going to write a1, a2, a3. And instead of b, we're going to write the coordinates b1, b2, b3. So we'll replace them. And voila, this is the equation of a plane in 3D. So the coordinates of any point on a plane equals the coordinates of a starting vector or an initial vector or initial point that follows the direction of two intersecting vectors that have already defined the plane. I hope this made sense, and we'll continue in the next video with the first examples. Bye for now.